So I'll just go ahead and get started. Like I said, I'll be talking just briefly about humic and fulvic acids in agronomy. Some of my experience with this is working with compost during my PhD as a soil chemist. So we were looking at attenuating or reducing impacts from arsenic and lead and some of the soils in central Washington that were sourced from historic lead arsenate pesticide use in the orchards. So there was a lot of mineralogy, organic chemistry that I was working on. But then this is extended into some of the work now with characterizing some of this material for manufacturers, even homeowners who do some of their own extractions with things like compost and mulches or whatever they're using. Some of these, was it Johnson-Su digesters, where you can produce a lot of these compost teas and they want to characterize it. A lot of it's the same sort of approaches. So just generally at Ward, this is part of the spiel that I typically am expected to do. So our services, we do everything from soil, feed, water, testing. Then it goes into more specifics like soil health, and then educational materials like soil sampling, looking at results, tissue testing, and it goes everything from agronomic applications to, we do a ton of research samples. A little plug, you get a 30% discount. If you do look for research, you need research testing done. We do everything from chemical, PLFA, microbiological, so it's and I do a lot of custom testing. I guess as head of R&D, I can do that. I really enjoy doing that. So if you have any questions, just reach out. We don't have the most advanced pieces of equipment. Probably the most advanced piece we have is a mass spec, ICP mass spec, but we do have GCs and everything else, all the standard equipment. So just throwing that out there. So some of the things I'll be talking about are, what are humic acids and fulvic acids, their production, both naturally occurring and then from a manufacturing standpoint, which is sort of the focus, its benefits, the chemical properties, some of the regulations behind it, because it is specific state to state. There are broad, federal regulations, but it's more specific on a state basis. And then some of the complaints or concerns, or I'd say downsides of some of these materials. And it's probably just as broad as its benefits. We probably know more about the benefits than we do some of the downsides, mostly because it's a lot of more research needs to be done on this material. So what are they? Humic acids and fulvic acids are essentially organic substances or compounds that are sourced from sediment, soil, and aquatic materials from the decomposition of organic matter like dead plants, microbes, metabolites. These are really enriched in organic matter in soils. Compost, things like that, it's mostly driven by decomposition of organic matter, and then they're naturally enriched through that process in these organic acids. Well, why are they, what's their function really, or why are they so sought after? I guess the crux of their reactivity are these reactive sites, compounds, reactive functional groups, carboxylic acids, phenolics, and quinones. I generally circled here. You can see they're just kind of dotted with all these functional groups. With that, they're very reactive, not just on a chemical basis, but on a biochemical basis. So they'll interact with microbes and roots. I think mostly microbes, especially in terms of some of their biochemical interactions, but also plants based on the hormones and some of the phytocompounds in these materials. I would say, broadly, they're not just organic acids. You're actually pulling out other things as well. Getting into more detail, and I try to keep the, I would say, quote unquote, scale of the two pictures here. On the left, it's a fulvic acid molecule, and then on the right, it's a humic acid molecule. I would say these are, I wouldn't say theoretical. We do have a lot of information on these, but because these are sort of defined by the chemical extraction, the way their solubilities, how soluble they are in a base or an acid during the extraction. It's also, sort of their chemical properties as well as how they're defined. It's kind of an interesting approach. It was based on sort of this historic characterization of organic matter in soils, specifically the humic compounds. And then going from fulvic acids to humic acids. So fulvic acids are the smaller, very reactive pieces. On the left here, you can see they're much smaller than a humic acid molecule on the right side. So as you go from fulvic acids to humic acids, from small to large, you increase in color intensity. If you do these extractions, which I'll just go into a little bit of detail next, you go from very light yellowish solution. Actually, these are sort of characterized by color. You know, if you do a humic acid versus a fulvic acid extraction, sometimes they're just based on color. And you can use a light source to characterize these materials in some cases, just shining a light through it. It is an absorbance kind of frequency you're looking at, but really it's the color that you can use to characterize these materials. You'll, as they get darker, they're much more enriched in humic acid. Black is the human or the insoluble compounds, separate from fulvic and humic acids. But they also increase in carbon and oxygen, molecular weight, solubility. So just sort of a broad way to characterize these materials, but they're fundamentally based up of fulvic acids and humic acids. And they have their different properties in the environment. So why do people like these? They do have a lot of historic application. I guess non-scientific and scientific. I said maybe non-scientific and then research-based applications. But broadly, they're known as osmoprotectants, which means that they will they help minimize the impact from environmental stress on the plant. So this is anything related to heat, water, or nutrient stress. They basically go after these oxidizers that are produced within the plant in response to environmental stressors, and they minimize, kind of like taking an antioxidant vitamin for humans. It's sort of the same thing. Somewhat, it sort of reduces the impact of those oxidizing stress on the plant. They also improve disease resistance. In the soil, they enhance nutrient availability as a chelator. The chelator grab onto nutrients for the plant. And they also improve soil structure. A lot of this is facilitated through enhanced microbial activity. So I would say it's very difficult, and I can understand sort of the complaints about some of this material is that a lot more research needs to be done, because a lot of it is based on fundamental biochemical mechanisms in the soil between plants, some physical properties in the soil. But broadly, we know that they do have a benefit. And then there's another wrench thrown into this, is that they're not all just humic and fulvic acids. There's also other plant compounds in these things, which can also, enhance or impair plant activity. So again, a lot more research needs to be done, but they do show promise in a field application, especially now with soil health being such a huge focus. And also if you're into organic farming, they are also more ideal. So in a natural setting, like I said, they are sourced from things like soil sediment, organic matter, just through the natural breakdown of that material of organic matter itself. They lead to the formation of humic and fulvic acids through that general breakdown process. But commercially, I would say they're more better known to be derived from things like peat, lignite coal, and shale, which are grossly enriched in these materials. And they are, I would say, probably easier to work with in terms of their extraction process. And it's more bang for your buck. If you're going to go into this to manufacture this material, you want a pretty hardy source. Using things like compost and whatnot, it's probably, you have to get a lot more of that material. It's a lot more energy dependent, I would assume. But for the peat, lignite, and shale sources, it's just an alkaline or a base extract. It just pulls out the humic compounds, and then from there it goes into acid and base solubilities, which will separate out the humic versus fulvic acids. So it's a pretty, I would say, not a very simple approach, but it's a pretty, I guess, standard approach in terms of these compounds. And again, this is just a diagrammatic outline. You have your organic source, whether it's shale, peat, lignite coal, or compost if you want to do this on a smaller scale, or I guess maybe more organic sources. You add a base to it, sodium hydroxide, for example, and then you'll separate out from that the humic substance, which is soluble, stays in the solution, versus the humin, which will precipitate out in that base. So from there, and the humin's the black stuff. From there, you add acid to the humic substance, which is floating around. And then from there, it'll separate out into fulvic acid, which is still in solution, and then the humic acid, which is insoluble. So it's really governed on solubilities based on acid and base solutions. It seems pretty simple. I would say it's probably one of the more simple concepts in some of these agronomic applications. But then its application is a totally different story in terms of its efficacy. And this is one of the examples. This is really probably one of my favorite things to really read about in this research is the other stuff in the humic and fulvic acids, because you're not just pulling out humic acids and fulvic acids. There are other things that are soluble and insoluble in those acids and bases, specifically plant hormones like auxins, gibberellins, and cytokinins. And then a lot of the research that has been done on this material, especially when they look at application of things like compost or vermicompost, some of these compost extracts, which is, a water extract of this material, they find in some cases that this stuff, even in the lowest dilution, they will actually get a response. It's really great for germination and then production. But even with that, you still get spotty results depending on the pre-existing environmental conditions. I would say the native fertility and some of the soil properties, which is the wrench in the whole system, is that you can't get predictable results. It really depends on your starting conditions. But even that's a big question mark, how that plays a role. But just to get an idea, just to give you an idea that this material isn't just organic acids purified. I mean, you can purify it, but in a lot of cases, they don't get all this extra stuff out. So you have other stuff in there, which is helpful. There's also the other part in terms of its production, specifically its regulations, because if it's humic acids versus fulvic acids, well, that's regulated one way. If it's phytohormones, all these other compounds in there, well, that's regulated a different way on a per state basis. So it gets really hairy really fast. So on a production standpoint, they have to be, I would say, as vague as possible, more broad in their characterization, because that kind of saves them in the long run. But there's still efficacy in the material. So the cost per acre, I thought I would break down a little bit. Humic acids and fulvic acids versus traditional fertilizers, just from some of the studies that I pulled. Just general on a per acre and then a per crop, you'll see that traditional fertilizers are generally lower across the board. And this is sort of understandable. The synthetic fertilizers, their production is much more streamlined and standardized. And then so humic acids and fulvic acids, because they're somewhat still, but I would say a novelty in some cases and aren't as widely used, they are a bit more expensive, and especially with their application, because you generally have to apply more, I would say, but you might have to apply it less frequently. So some of these trade-offs. So it is more, I guess in terms of the yield, which I'll go to the next one. And again, this is just I assume, what are these going to be posted on the website, Carol? The slides, I guess.
So the recorded talk will be available on the PNW Farmers Network YouTube channel.
Okay, perfect. So they can come back and reference this if they'd like to.
Absolutely. Thanks.
And then for the for the yield component, which is sort of like, the takeaway really, it's been generally shown that you do get even to higher yields. Again, this is the big question mark, is that in some of these studies where they compare these humic acids and fulvic acids to traditional fertilizers, it's still quite varied. Really, from what I've seen from growers that I've worked with, is that it comes down to what they want their inputs to be and what product they want to produce. So if they want to go more conventional, that's the path they take. And so it's more of a yield-driven, I guess, agronomic production setup. If they want to be more, I guess, sustainable, which is a big drive right now with soil health, they tend to lean more on these humic acids and fulvic acids, and some of them find very good use with them. I think it comes down to really how sustainable the grower wants to be in terms of their production, and I guess sort of that brand that they want at the end. The big push now is soil health, so this is really coming up more and more now. But you can see it's, I would say, comparable yields in most cases, so it could be quite useful. And again, you're applying this less frequently than a fertilizer, so you'd have to look at the end, your per acre profit in terms of your yield and cost per acre. Some of the laws and regulations, this is a big one, going to a lot of these conferences where people are producing these biostimulants, like humic and fulvic acids, some of these phytocompounds, nitrogen replacers, inoculants, things like that. Per state, it really varies from very strict to very lenient. I mostly outlined the Washington State one, and it's regulated under the Washington State Department of Ag, and they have a very detailed path you follow in terms of production of this material. It has to go through registration, labeling, all the product claims, inspection. The inspection is on their part, so they could always come in and inspect the materials, and then post-application if they feel the need to. They do this with anything, fertilizers too. If you're going for more of an organic certification, that's its own process. And then the guidelines and special licensing. I would say this is probably more standard than anything for most of the states. Just a few other states, California is very similar. They have very strict biostimulant guidelines as well. But for Texas, they focus more on environmental harmful substances. So it's not as strict, I would say. Florida is much more lenient. They look more for the nutrient content of the product. So it's very broad in terms of their characterization of the material. And then New York, it has to go through initial testing before they can, you can actually get any sort of labeling done or registration. So state to state, it's very subjective. But I would say fundamentally, from what I've seen so far, the hormone part versus humic and fulvic acids is really sort of some of the things that sort of parse out how you're going to label the product. Because if you are going to say it's a biostimulant with phytohormones, well, that's much more stringent. So again, they fall back to just saying humic acids and fulvic acids, which they can because this is just a simple acid-base extraction. So they can actually say that. They still have to get it characterized though. So criticisms and concerns. I would say the broad one is, some of the spotty results, but potential phytotoxicity. This is really with any sort of amendment, any sort of fertilizer. The poisons in the dose, according to Paracelsus. So with this one, this usually occurs from over-application. Again, that's the same with anything. Some of these materials are salty, I would say, because it is an acid and base extraction, usually like a sodium base. So they can be a little bit salty. The salt probably, I don't know which would cause more of an issue, but I would say the salt is definitely a big problem. Inconsistent results across the board. This is what I continually hear. Some people say this didn't do anything. Some person said I got the biggest yields ever. So a lot more research needs to be done on that. I'm sure people probably in the panel know, or on the webinar probably know more about this than I do. Quality control, the standardization of the product in terms of its, characterization, disclosure. A lot of the stuff is proprietary. That really bothers me. At least at Ward, we try to be as open as possible about any method, give you all the information you want. But some companies are very onerous about their materials, especially if you're making a product, which is understandable. But because of the spotty results, it really just adds more of a veil to anything. Economic factors, the cost, and then the benefit per yield, per acre on a yield and application basis. That's really something that you have to do in terms of your own research. And you should always start out with trials, never just jump in, even with anything. Even if you go from tilled to no tilled, any sort of agronomic practice, you just test it first and then just see if it works for you. And I'm sure, like I said, more people know about that than I do. Limited research, it's still ongoing in many cases. And I think it just shows out how little we know about a lot of this stuff, because it still falls into that plant versus microbe sort of interaction, plant versus biocompound interactions, biosignalers, hormones, steroids, all that stuff that are coming from this material, and how the plant and the general environment will react to it, and how that translates to yield and production. And then the regulatory issues, again, it's pretty spotty from state to state. But again, that falls back to how little we know about this material in terms of its production and application. And then the conclusions, they really do hold very good promise for application on a field setting. Would really like to see more in terms of the different sources and that sort of efficacy, because I see a lot of research done on some of these extracts from compost, thermophilic compost and some of that, versus like the mining of the materials. I'm not a big fan of mining, but I know we need it to survive, because we all benefit from it. But I would say one, if you're going to be sustainable, one is definitely more sustainable than the other. So that's just my soapbox. and then the lack of standardization in the commercial products, and then the conflicting results. That is another big issue that we are still trying to battle with, is to figure out when, where, and why, and how the stuff works and why it doesn't in some cases. It's really interesting if you're a scientist. It just adds more questions to anything. But as long as we keep pumping out more research, I think we'll hopefully get to the bottom of it. Although we know a lot about it. It's just when it works and when it doesn't, those are the big issues. And then ongoing and future research aims to address these gaps, like I just said. So I'm looking forward to more research coming out of this, especially as we get into finer detail in our scope in terms of some of biochemical interactions. And again, a lot of it leads into the soil health boom that's going on right now. And so I'm excited about it. I think it will really give us a lot of information in terms of some of those interactions between the root zone and then microbes and that whole exchange, and then also the benefits of that, in terms of production, yield, environmental quality, and then all of my references. So that's pretty much all of it.
Great. Thanks for such a wonderful, informative talk, Dr. Freese. You really touched on a lot of really important factors within the soil, both the soil chemistry and the fertility and yield impacts, but something that, and also what a great nod to trying things on individual farms. For more inspiration on that, we have a podcast with the Farmers Network, so a little plug there. Thanks for that. And I appreciated your nod to if you're really thinking about big picture sustainability, it sounds like a lot of the materials that the organic acids are currently being extracted from are mined. So thinking about how we move more from a mining linear cycle to maybe more of a nutrient cycling sort of system with that, as we consider life cycle analyses of these products to make them more sustainable. I heard that nod. So, and actually we've just got questions coming in on the chat, so I hope you're ready.
Oh yeah.
Great. Thanks for the first question, Gio. Could you explain the process of how humic and fulvic acid complexes with nitrogen, like UAN32 fertilizer? An example, adding fulvic humic acid with winter wheat chemistry and nitrogen reducing foliar leaf burn.
I would say, just from a general chemistry standpoint, I would say it would have to be the organic acid sites, the carboxylic acid groups, and then some of the amine groups would be maybe the points of contact, depending on sort of the soil pH. Of course, it could also be what's also known as like cation bridging. So some of the minerals in the soil fundamentally will act as a bridge between some of the humic and fulvic acid compounds, and then also some of the nitrogen compounds. I would have to really see some of the actual chemistry of each to see how they're connecting up. But just generally from what I understand, between two organic compounds, typically you have to have a bridge. Either that's, a mineral like a iron, manganese, even calcium, although iron and manganese and even aluminum will act as a better bridge. And then also the hydrogen, so protonated nitrogen groups on amines can act as a bridge as well, or a complexing area, but that really depends on the pH. Even for all of that, it depends on the pH. That would be my guess. I'm not sure how much more information you would want about that, though.
Well, one thing I know to be true is that soil chemistry is a rabbit hole that I think never ends. And I continue to appreciate your depth of understanding around that. And actually, I'm not sure, Gio, you are welcome to unmute and ask any follow-up questions, or we can segue into what is a pretty good next question that relates, I think, to that. Gio? And actually, if you want to stop sharing your screen, we can kind of go into the more of a conversational.
There we go.
Great, thanks. So Dr. Antonangelo follows up with any insights or potentials on the use of humic and fulvic acids to complex and immobilize toxic aluminum in the acidified soils in Washington and eastern Washington, northern Idaho.
Yeah,
that's other parts of Washington too.
Yeah, no, that's really interesting. I was actually working with one of my committee members, Dr. Tara Sullivan, one of her graduate students, on aluminum toxicity, when that's exactly what you worked on too, Carol. So you know quite a bit about that. But it's kind of interesting because from what I understand, and I'm not a plant physiologist, but from what I understand, the plants will exude low molecular weight organic acids as a stress response to aluminum in the environment, which is a complexing reaction, reduces the toxicity of it. I would say in this case, it's really interesting because I don't know, whenever people talk about applying this, it doesn't sound like they're really applying enough to act as a complexing agent, at least to get to the root zone enough to really reduce toxicity. I would say in some cases, if you're applying it, you're really stimulating a reaction in some cases to where, either the roots are exuding something or you're enhancing microbial activity, which will then, kind of promote the relationship between root and plant. I would say you could, as an injection, you could probably inject it. I don't know. That gets into some pretty hairy chemistry as well, because the humic and fulvic acids, they don't just interact, on a chemical basis, they don't just interact with positively charged ions like aluminum, iron, and some of those things, which could reduce the toxicity. They will actually enhance the release of some other compounds. So things like phosphate, sulfate, some of those things that might also then interact with things like aluminum and iron. So really, if you apply it, you would really have to see, because it's what I learned is that you can't say, yes, this will happen. If you add this will happen, because 50% of the time, if not more, you'll get side reactions that were very unpredicted. So I would say it's worth looking at. It would be a very useful, I thought about, the application of organic acids just for reducing aluminum toxicity, if that would be useful in any case. If you could actually do that, I would say it's worth looking at for sure, but how much you would have to apply and what side reactions will come from it. I'd probably say I'm more curious about that, because I've seen that happen so many times in soils and soil amendment research. But yeah, I would say on paper, it sounds like a very promising thing.
Great, thanks. Ooh, more potential for research, always.
Always.
So we've got a couple more questions coming in. I do want to make sure that we have at least 10 minutes for breakout rooms as part of the coffee hour today. But could you compare relative quantities of fulvic acid and humic acid in soils naturally versus what you might apply commercially? So thanks, Dr. Huggins, for that question.
Yeah, I think it's, oh gosh, I had all this. Yeah. I would say for humic acids and fulvic acids, oh gosh, it's on a percent, just low percent basis. It's very low. It really depends on the organic matter, but I think it's in the single digit percentages, if not lower than that. Just from my work with compost application, I don't think it's very high. I would have to pull the numbers for that, though. I have it in some of the papers I'm looking at. But from what I've reviewed, it's in the single digit percentage basis, if not lower than that. But I'll look and get the actual numbers for you.
I've got a question. Can people follow up and contact you after this as well?
Oh yeah, this is pretty much what I do all day, is work with researchers and try to get information for them and do lit reviews and all that stuff. There's so much to look through, though. It's always like I always miss something and I have to go back and pull more information.
And producers too?
Oh yeah, everyone. Yeah, I do a lot of research support for the growers, and then also who do a lot of this research, and then also the people making the stuff. So
awesome. That sounds like a lot of fun. Dr. Politz asks, do they add phytohormones to the formulation, or are they naturally present? And do they have analytical evidence that these are in the formulation, or do they just infer from growth promotion?
I think, yeah, for the studies where they apply this, they do have evidence that it's in the material. So I'll say, without adding it, it's in there as a byproduct. And even with the mine stuff, they still say, or the mine materials, they still say it's present in those compounds, which I kind of find sort of surprising, because I wouldn't really think it would be, but it really depends on the source, I would assume. They broadly just said that, yes, it comes from those sources as well. I would assume it's not in very high concentrations. But in some of the production that I've read, production materials, some of them do promote that. They will either add it as a kind of an added benefit, or they'll actually analyze and say, yes, it also has this and this and this. But again, it gets into that regulatory issue. And that's from a lot of the producers of this material. That's the thing that they want to avoid, is the regulations. So they'll fall back to say, they'll tell you, yeah, we think it has this in there, wink, wink. But they will fall back and just say, but it's humic acids and fulvic acids. And that's just generally from what I understand.
Great. And one more question, and then really we'll just have a few minutes for breakout sessions, and then come back before we depart today. So this is the question of the hour. How about using humic acid as a way to reduce synthetic fertilizer, complexing the nutrients such as nitrogen to prevent its loss and more slow release? So thank you, Craig Madsen, for that question.
Yeah, I would say that's really the push for a lot of this. So when people, so we work with a lot of the larger consultants who are pushing a lot of the sustainable approaches in ag. And a lot of that relates into like carbon stocks, carbon budgets, the whole carbon market. It all falls into that because soil health is the crux of all that. If you want to build up your carbon stocks, you need a healthy soil because microbes are doing all that work. And so for that. So with the application of humic acids and fulvic acids as a fertilizer replacement, it acts as a chelator. It can promote the chelation and release of nutrients. But I would say in terms of some of the organically sourced things like nitrogen, from what I understand, it really is facilitating sort of the buildup of some of those microbial root associations, the general soil microbiology. A lot of it is coming from the hormones because these humic acids and fulvic acids, I think specifically some of the fulvic acids act as biosignalers, which will promote that sort of interaction. And then that helps, and that whole thing is mediated, the whole root microbe interaction is mediated by these biosignalers, root exudates and things like that. So I think it sort of like amps up that quite a bit. And a lot of this is theoretical for me still. The research is so detailed, it's really hard to extrapolate a lot from it. But I would say in that case, I don't think it's really supplying nitrogen unless you're adding nitrogen to it. I don't think the nitrogen is terribly high in this material. I wouldn't say it's high enough to really be a good fertilizer source replacement for nitrogen, but I would say it in terms of chelation, sort of ramping up some of those other processes that, and that's what soil health is. It's all about function, is enhancing some of those processes that will help facilitate the release of things like nitrogen. I think that's really what some of the more beneficial aspects of that would be.
Yeah, I'm hearing in the question and with some other thoughts is just how do we get the most out of the nitrogen we are putting down? And so are we having to put more nitrogen, in the tank, in the ground, just to account for some loss? Or, can we reduce the amount that we're putting in the tank, and with the idea of humic acids helping us and fulvics helping us hold on to that a little bit longer in the soil? So I don't know if that's the crux of the question.
Yeah, I would say, I guess mostly in those cases, because the nitrogen is sort of mediated in terms of what the plants need. We tend to oversupply, we just base it on a yield and you just, add it incrementally. But I would say in a lot of these cases, the plant can mediate this if you support that process, the whole root rhizosphere, soil microbe, interactions. If you're supporting that process, the plant can get what it needs. And you have to do kind of supply those nutrients as well, but don't oversupply because that will also impair some of that function, that root, the root rhizosphere function in terms of how it facilitates and coerces microbes to come in and help it, supply it with nutrients. So I always say I would never go into this research because it's so hairy. I always appreciated mineralogy and soil chemistry. It always got really scary as soon as you threw in the microbes. It's one of those things, but I'd say it's really fascinating. And so I really like the research that people are doing on this.
Very different than test tube chemistry. Okay. I did suggest that we had the last question already, but Aaron looks like he wanted to make sure I got in when would you apply a humic versus fulvic acids? Aaron Esser. When would you apply humic versus fulvic in wheat?
Oh, in wheat. I would say because some of these products, they do, from what I've seen, they mostly promote the humic acid side of it. I think the humic acids, because they're more, I would say, probably long lasting in the environment versus a fulvic acid, because the fulvic acids are lower molecular weight. They are, probably metabolized a lot faster. But I think the humic acids do have an appreciable amount of the biosignalers, the larger molecular weight, hormones and things like that. I would say you would have to apply it. From what I've seen, they apply it at germination or like pre-germination. So because they have shown, and a lot of the studies have shown that it actually promotes germination and then continual production. So how much you apply is really based on what you're seeing on site, and then also the fertility management that you're going by, the soil fertility assessment that you're doing. and any sort of, other goals you have like yield, production. But I can't exactly say when and how much. But really, the humic acids, if I was going to do it, would be the fallback, knowing that there's other stuff in it. I mean, it's not just pure stuff. But that's kind of, from what I've seen, they really push that component for those reasons.
Great. Thanks for that. Okay, we're going to stop there for now. I love the interest in this. It sounds like, all the momentum. Maybe we'll have to go deeper into this topic in another coffee hour. But right now, I'd love to send you all into breakout rooms for about 10 minutes. And thanks for coming. Please do stick around for the breakout rooms, because that's another good chance to talk with other experts in this type of topic about their perspective on this. So with that, thank you again very much for that talk, and we'll be back from the big breakout rooms for the main session in about 10 minutes.